So we have a potter's wheel, big old solid disc, rotates. It's freely rotating at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim and exerting a radially inward force of 70 newtons. Find the coefficient of kinetic friction between the rag and the wheel. So I'm going to draw the wheel as if we were looking down at it. So here's our wheel. Has some radius r, mass m. We know the radius, we know the mass. It's initially rotating at 50 revolutions per minute. The potter comes in, has a rag. I don't even know how to, there's my ugly rag. I don't know how to draw a rag on there. If the potter pushes in with a force of 70 newtons, then he can bring this wheel to rest in 6 seconds. Now we're going to assume that that angular acceleration, the rate at which it slows down at, is constant. Okay? If he's constantly pushing the 70 newtons, then the deceleration of the wheel will be constant. Alright, so we know there's a net torque acting on the wheel. We know that because the wheel has an angular acceleration. If a wheel has an angular acceleration, that means its rotation rate is changing. So it was initially rotating at 50 revolutions per minute. It comes to rest, so the final rotation rate is 0. So there was some sort of angular acceleration that caused that. We can look at our kinematic equations. We have a nice relationship between rotation rate and angular acceleration and time. We do need to be careful though. In this equation up here, when we relate torque, moment of inertia, and angular acceleration, without exception, angular acceleration has to be in radians per second squared. Period. End of story. It cannot have any other units. Okay? So to get radians per second squared for alpha, we need this to be in radians per second. But that's easy enough. 1 revolution is 2 pi radians. 1 minute is 60 seconds. So let's see, that goes into there. 30, the zeros will cancel. So omega naught will be 5 pi over 3 radians per second. We know the final angular speed is 0 because we are told that it comes to rest. So solving for alpha, alpha will be negative omega naught over t. Make sure these are... So our angular acceleration is negative 5 pi thirds radians per second over time, which is 6 seconds. So 5 pi over 18 radians per second squared. So our angular acceleration we're able to find from the kinematic equations. Questions on coming up with that? Is that part okay? Angular acceleration is negative, which should make sense. Counterclockwise being positive, and negative angular acceleration, if it's opposite the angular velocity, then it's going to slow it down. So the net torque. What force is causing the torque that's making this wheel slow down? Friction. Exactly right. As the potter pushes into the wheel, he's generating friction between the rag and the wheel. So So there's a force of friction between the rag and the wheel, and it's that force of friction that's making the wheel slow down and come to rest. Force of friction, we know, depends upon the coefficient of friction and the normal force. Now in this case, it's not the normal force from the ground pushing up on the whole setup, because that's not the normal force that's causing the object to slow down. What normal force is actually causing this friction to exist?
Normal force on the wall.
Right. This 70 Newton force that the potter is pressing against it. So that is our normal force. Okay, so torque. We know the net torque is equal to I alpha, but in general we know torque is equal to a lever arm times the perpendicular component of the force. So if we were to draw our lever arm here, it has a length of r. The perpendicular component of the force is friction, and conveniently the friction is already perpendicular to the lever arm, so we don't have to find components. Now, this torque is negative. If you just imagine friction being the only thing applied to that wheel, it would make the wheel rotate clockwise, which is a negative torque. So that torque, that is the net torque. There's no other forces causing torques. There are other forces. There's a force of gravity, but it's not causing a torque. It's acting at the center of mass, so there's no lever arm. So friction is the only one causing the torque, so that torque of friction needs to equal I alpha.
And it's negative because it's opposing the motion, right?
Negative torque because it would make it rotate clockwise.
Right.
Yes.
Oh, I see. Okay.
So the force of friction, like we said, is equal to the coefficient of friction times the normal force, which we know is 70 newtons. I, moment of inertia. What type of object do you expect a big potter's wheel to be? Solid disc. Something like this, only much bigger and more massive. Solid disc off the table in our book, the moment of inertia of a solid disc is 1/2 mr squared. We know the angular acceleration, we've already calculated that. This r will cancel with one of these. So we find that mu is equal to, bringing the negative sign over, negative mr alpha over 2 times the normal force. Negative. Our mass is 100 kilograms. Our radius is 1/2 meter. Alpha, we've already calculated, negative 5 pi over 18 radians per second squared. Normal force, 70 newtons. The negative signs are going to cancel, which is good. It doesn't make sense to get a negative coefficient of friction. So I get 0.31 units. Remember, a kilogram meter per second squared is a newton, so the newtons cancel. Technically, we're left with radians there. Radians are not a true unit. They're more of a clarifier. They can be there or not be there. So we don't tend to write the radians here tacked on as units. That's our coefficient of friction.